Hi, I'm Aaron. To save time and also myself from repeating the most obvious elements that make a graph, all the graphs I mention and go into detail about all have edges and vertices. A simple graph is a graph that does not contain weights, directions, loops, or multiple edges. The main number of edges with n vertices is given by the formula n open bracket n minus 1 close bracket divided by 4. Similar to a simple graph is the simple multigraph. However, simple multigraphs do contain multiple edges. Nevertheless, they still do not contain weights, directions, or loops. Different to the two graphs just described are the directed graphs and undirected graphs. These two graphs can contain loops and multiple edges. A directed graph is a graph that has edges that are directed from one vertex to another and can be defined as G equals brackets n comma e close bracket, which consists of the set n of nodes and set e of edges, which are ordered pairs of elements n. Similar to the directed graph is the undirected graph. This graph contains edges that are all bidirectional, meaning all edges are directed in both directions. The undirected graph can be defined as G equals open bracket n comma e close bracket, consisting of the n of nodes and the set e of edges, which unlike directed graphs are unordered pairs of the elements n.
Euler paths and circuits visit each edge of a graph exactly one time. An Euler path includes all the edges exactly once and begins and ends with different vertices. The start and finish points of the path are vertices with odd degrees. The start and finish vertices are the only vertices that do not have an even degree in the graph. As shown in graph G, the paths begin at vertex 1, which has an odd degree of 1. It continues to visit vertex 2, 3, 4, and 5, and then returns to vertex 3 as to satisfy the condition of using every edge. Like the beginning vertex, the end vertex 3 also has an odd degree, being 3. To turn this graph into one which has an Euler circuit, all vertices must be made even. To do this to graph G, we must add a new edge connecting vertex 1 to vertex 3. This new edge has given these vertices even degrees, meaning a circuit can now be made. Starting from vertex 1, the circuit may travel to vertex 2, then 3, 4, 5, back to 3, and return at vertex 1. As shown, an Euler circuit must start and finish at the same vertex, unlike the Euler path. The origin of Euler paths and circuits comes from the historical problem, the Seven Bridges of Königsberg. This problem was analyzed by Leonhard Euler in 1736. The problem laid the foundations of graph theory. Euler's problem was that he wanted to be able to cross each bridge one time without revisiting any of the bridges. As shown, each landmass can be viewed as a vertex and each bridge an edge. From his work, Euler deduced that it is a necessary and sufficient condition for the Euler path that the graph is both connected as well as having either 0 or 2 nodes of odd degree.
Hello, my name is Scott, and today I will be talking about Hamiltonian paths and cycles. Hamiltonian paths and cycles are a part of graph theory. A Hamiltonian path is an undirected or directed graph that visits each vertex exactly once. A Hamiltonian cycle is a Hamiltonian path that is a cycle. This means that the start and end points are visited twice. Hamiltonian cycles and paths all have certain properties. Any Hamiltonian cycle can be converted to a Hamiltonian path by removing one of its edges. A Hamiltonian path can be extended to a Hamiltonian cycle only if its endpoints are adjacent. Hamiltonian paths and cycles are much more difficult to prove than Euler paths. One theorem, notably Orr's theorem, gives us a sufficient condition for a graph to be a Hamiltonian path or cycle. It states that a graph with sufficiently many edges must contain a Hamiltonian cycle. The theorem considers the sum of the degrees of pairs of non-adjacent vertices. If every such pair has a sum that at least equals the total number of vertices in the graph, then the graph is Hamiltonian. The image here shows the formal statement for Orr's theorem, where G is a simple graph with n greater than 3 vertices, and V and W are non-adjacent vertices.
Hello, my name is Luke Ross, and today I'll be talking about spanning trees and minimal spanning trees. Spanning trees are very useful when planning networks. The kind of network does not matter, has applications in computers and power grids. Anything where lots of people, houses, even smaller networks need to be efficiently connected. These networks can be modeled as graphs. The locations can be considered as vertices, the connections between them edges, and the cost or difficulty of the connection, the weight. A spanning tree may then be constructed, and then to determine the easiest or cheapest way of implementing the network, the minimum tree can be found. Spanning trees are also useful for navigating networks with redundancy, the most practical examples being computer networks and power grids. There may be multiple paths from the current location to the destination, so to use the least congested or shortest route again involves finding the minimal spanning tree. There are two algorithms to find such a minimal spanning tree. The first I'll talk about is Kruskal's algorithm. On screen, we have a graph modeling a power network with our wiring in kilometers. What Kruskal's will do is pick the lowest weight edge anywhere in the graph, as long as it does not make a cycle. Once all the edges have been picked, such that any other edge being picked will make a cycle, we have the minimal spanning tree. The other algorithm is called Prim's algorithm. It's similar to Kruskal's, but instead of picking any graph, we pick a starting vertex and pick the lowest edge that's connected to it. Then we can pick the lowest weight edge from any of our vertices that are already in our graph, as long as they don't make a cycle. Again, once we have picked all our edges so that they don't make a cycle, we have our minimum spanning tree.